we pick the best 300,000. In fact, we pick every star in the field of view that could yield a habitable Earth-like planet. Of those 300,000, we will put them in order of priority, and we create a list of 150,000, approximately 150,000 that we will observe at the start of the mission. As the mission progresses and the spacecraft drifts away from the Earth, there might be a window of time when our transmission rate decreases to a point where we might have to down-select some stars. We might have to go to 100,000. That's why we have these numbers floating around there. But at the start of the mission, we're going to look at about 150,000 stars.
Thanks. Patty was telling me, I guess yesterday or sometime this week, half of 1% is the probability of a properly aligned star around the proper alignment around the kind of star you would expect. Is that where the hundreds of possible discoveries comes from?
That's right.
Okay.
The sun's diameter is about 100th of an astronomical unit. And the probability is simply the diameter of the star over the diameter of the orbit. Diameter of the orbit is 2 AU, that's 0.5%.
And that's for a system that's exactly like the Earth and the Sun. It varies depending on the actual details of that system.
Right, I understand. Thank you. And my last question was, all the big exoplanets found close in, obviously that could either be that's a standard way solar systems are put together, or it could be an artifact of the way we discover them, right? I mean, will Kepler resolve that question one way or the other? I mean, we've been talking about Earth-like planets, but obviously you're going to see a lot of Jupiters too. Mm-hmm. Will you be able to resolve that about the fundamental nature of, if there is one, about how solar systems are put together?
I don't think so. We will get more clues, but it's always sort of a mystery. And every time we've looked, we've been surprised. We knew the orbits had to be circular, but they turned out to be elliptical. We knew Jupiters have to be at 5 AU. They're many of them within the orbit of Mercury. But when we got these facts, we put them together, the theoreticians said, oh, what that must mean is that the giant planets form where there's a lot of material, they spiral in, they give up their momentum, they give up their energy to the accretionists by forming a wave, and they come falling inward. And we find something like 5 or 10% of the stars have these giant planets. The rest of them don't. Now, does that mean the giant planet came in, destroyed all the small planets, and that was only 5% of the time? Or did the other 95% also come in, but didn't stop? They fell into their star. In that case, if that's the case, there aren't any Earths. So we really don't know. The theoreticians are asking, give us more clues, give us more information, and we will build better theories. But no matter what we give them, there's much more to learn about what we're finding out there. If you look at the giant planets, we found 340 of these. And you'd say, why would you need any more? Well, it's something like, asking Darwin, he's seen a bird, he's seen one finch, he's seen a beak. Quit? No, you need as many birds as possible to understand these giant planets. So my guess is by understanding giant planets and small planets, we're going to make dramatic discoveries about other planetary systems. But I don't expect that we're going to have all the answers in 3.5 years.
Let me add one thing, Bill. You hinted at something in your question itself. I mean, one of the reasons, perhaps the main reason, we found so many huge planets so close to the stars is that the experiments that were used to find those were designed to find exactly that. Those are the easiest ones to find. You will find large planets very close to a star because they will have a gravitational tug on the star or radial velocity change. Kepler is not designed to find Jupiters like we have them in our solar system because it's only a 3-year mission. Jupiter would transit once every 5 years. I believe the period's 5 years roughly? 12. Yes. 12 years. Once every 12 years. It's 5 AUs. Had one number right. So, we've got one example of a solar system that has inner terrestrial planets and outer planets that are gaseous. One example. And we didn't find any of these with these other methods because they're really not designed to find them. Kepler's not going to be able to prove that solar systems like ours are common in terms of Jupiters and Uranuses and et cetera. But it will be able to disprove one conclusion from those early results. Oh, there must not be any Earths or very few Earths because these giant planets eat them all up. If we find that 1 in 10 or 20 or 30 of your stars have Earths, that kind of gives us another point to throw out that current theory, yes, which hopefully you will. But anyway.
Todd? Todd Halverson of Florida Today, for whoever wants to field it. I'm wondering if you could elaborate on how you might be able to use either ground-based telescopes or other orbital assets to follow up on any interesting or compelling findings that you might have during the mission?
I think I can answer that one. Basically, when we find these sets of transits that we're looking for, we're sure they're not spots. But what if you were looking at a large star and a small star is orbiting it? So one of the quickest ways to tell the difference there is to take a ground-based telescope with spectroscopy, and it'll show that there's a lot of radial velocity of that main star. And that says there's a stellar companion. It's not a planetary companion. If it's a Jovian-massed planet, some big telescope like Keck or HET can say, I can measure the mass of that secondary. I can get the mass of your Jupiter. If the mass is even smaller, like Earth, in the habitable zone, that's too small. We can't tell for sure, but we will check that it can't be anything else. So there are a number of things the ground-based telescopes are used for to confirm what we're finding. Sometimes we can say we measure the mass of the planet. Sometimes we can say whatever is there has a very small mass, just an upper limit. And an instrument is being built at Las Palmas in the Canary Islands that will actually do better. It'll allow us to measure masses of smaller planets. And of course, the JWST and Spitzer can actually see the transits of these small planets, so we can get confirmation in coming years for these planets. But we need the ground-based system.
You're in the front.
Timothy Ferris, National Geographic. How many of these stars, now you've done a census of them and all, are sun-like? In other words, just if you're putting a catalog, say, of spectral types, how many of them are solar-type stars?
I had that number written down and I didn't bring it. But I can say that we have a count of the number of stars for which an Earth-like planet in the habitable zone, so an exact Earth-Sun system, is detectable in the transits and can be followed up by ground-based observers. It's bright enough. And that number turns out to be about 15,000 stars.
Jim Siegel, Celebration Independent, for whoever wants to answer. I have three questions that kind of build on each other. The first is, what happens to this satellite after 3.5 years? Does it remain operational? Does it drift into space? Does it fall to Earth? What happens to it?
It's actually designed so that it has plenty of expendables to go 6 years. And that's important to us because to get 3 transits, we need 3 transits for confirmation. As we go to stars hotter than the Sun, that habitable zone moves further and further out, and the orbital period required moves further out. So in 6 years, we can actually study the habitable zone of planets hotter than the Sun. But the other aspect, of course, is since we're in orbit around the Sun, and it's like a 53-week orbit, it leaves the Earth week by week. Each year, it's back further by a week. So after something like 56 years, it's returned. My expectation is that 53 years from now, mankind's capability will be such that we can go up there and we can pick it up and we can put it in the National Air and Space Museum, and that the National Air and Space Museum at that time will be on the moon.
Okay. Question 2 out of 3. Let's say that we're all back here in 3.5 years. I'm interested in what sort of information you would report back to us. Can you kind of project yourself 3.5 years from now? What sort of information would you come up with? Would you tell the world and tell us?
You want to take that one, Natalie?
Again, the main objective is to be able to tell you what the frequency of habitable Earth-sized planets is. Rocky, habitable planets, places where liquid water could exist. Of course, there's going to be a lot of other results to report as well. As been mentioned, we're going to be detecting giant planets. We're going to be detecting lots of systems that we've never seen before that we're going to be modeling that are completely new. But that's our primary objective, and that's what we'll be hopefully giving to the public in 3.5 to 4 years.
And then lastly,
Go ahead. Go ahead.
The question of the frequency of habitable planets is obviously the one of greatest interest. But beyond that, just the question of how often does nature like to make terrestrial planets around a star will be